This is the first of two lessons on the photoelectric effect. So evidence started to accumulate near the end of the 19th century, particularly when Heinrich Hertz in 1887 experimentally found that electrons were being emitted from metallic surfaces. So 1887, German Hertz found electrons. So in an experiment, he found that electrons, when he shone light on a metal surface, electrons were emitted. And I should mention he used high frequency light, so high energy light. And this is known as the photoelectric effect. Photo means light, and electric is to do with electricity. So he found that you would get electricity from shining light onto metal surfaces. And ironically, this is whilst he was conducting experiments to confirm the existence of electromagnetic waves. So pretty strange at the time as to what was happening. I'll draw a diagram of the photoelectric effect. So suppose you have a metal like sodium and light was shown on the sodium. Electrons were found to be ejected from the metal. Now this is inconsistent with the wave model of light. Just like the black body radiation problem. And following Hertz's work, there were also other experiments conducted over the years. And these were some of the observations found from the photoelectric effect. The first one was the existence of what's known as the threshold light frequency. This was the first of a series of observations. So what was found out was that if the frequency of light, so f of light, was below some specific threshold frequency, some maximum frequency, f sub naught by convention, that implied that no photoelectrons, so electrons emitted due to light, no photoelectrons emitted, okay, from the metal surface. And this threshold frequency, f sub naught, is actually characteristic of a metal, regardless of how bright, how intense the light was. So, for example, sodium has a threshold frequency, f sub naught, of around 0.8174 times 10 to the 15 hertz. Copper, 1.376 times 10 to the 15 hertz, and so on and so forth. Okay, so different metals have different threshold frequencies. And this observation is inconsistent with the wave model because classical wave theory relates the light intensity to the wave amplitude, not the frequency. But in this case, frequency is involved in the process. And you must satisfy this specific threshold frequency in order to get photoelectron emission from the metal surface. So inconsistent with wave model because according to the wave model, the classical wave model, light intensity, as I mentioned, is related to wave amplitude. Okay, the bigger the amplitude of the wave, the more energy, the more intense, right? But this is not true according to what we see in reality. So that's the first observation, the observation of a threshold frequency. Second observation is the instantaneous emission of electrons at low intensity. So for frequencies greater than the threshold frequency, Electrons, you've automatically got electrons emitted, so electrons immediately emitted. Okay, you get photoelectrons emitted from the surface of the metal, even with very low intensity light. Okay, but classically it takes time for electrons to absorb energy because the energy is spread out across the wavefront, right? But in reality, we see instantaneous emission. So that's also inconsistent with wave model. Okay, and I'll write delay. Okay, there should be a delay in the emission of photoelectrons. And the third and final observation of the photoelectric effect, maximum kinetic energy of photoelectrons. So it turns out that the kinetic energy, the maximum kinetic energy of the photoelectrons is proportional to the frequency of incident light. Okay, this is experimentally shown. This is inconsistent with wave theory once again, with the wave model. Okay, because the wave model incorrectly predicts that the energy of the photoelectrons from the surface is proportional to the light intensity and not the frequency. So they're the three main observations associated with the photoelectric effect. Then came along Einstein, Albert Einstein. I'm sure he doesn't need an introduction. World-renowned theoretical physicist, Nobel Prize-winning physicist. Einstein in 1905 wrote a paper on the photoelectric effect, and he basically extended Planck's idea. So he took Planck's idea one step further, Planck's idea of energy quanta, and he applied it to all electromagnetic radiation, EM radiation, i.e. light. And he suggested that electromagnetic radiation is quantized and is made up of a stream of particles later called photons. So light, or I should say EM waves, are made of photons. Photons are particles of light. And they had energy. Okay, they have energy given by Planck's equation, as we've seen before. E equals HF, where E is the energy of the photons, measured in energy of the photon, I should say, measured in joules. H is Planck's constant, it's a number, 6.626 times 10 to the minus 34 joule seconds. And F is the frequency of the photon given in hertz. We can also express the photon energy E in terms of the light's wavelength, lambda. Let's see how. So E equals HF. Now we know from classical theory that the velocity of a wave is given by its frequency times its wavelength. Now for light, because electromagnetic radiation travels at the speed of light, we can replace the V with a C for speed of light. So that's equal to F lambda. Let's rearrange for F. So F is C over lambda. So we can plug in C over lambda for F. So we get HC over lambda. So this is the energy of a photon in terms of its wavelength, where C is the speed of light. It's 300 million meters per second. And lambda is the wavelength of the light measured in meters. And in today's picture of light, we find this wave-particle duality. And I should mention that Einstein was actually right. Okay, light is made of packets of energy, photons. So this wave-particle duality of light exists. And in other words, light is neither a particle nor a wave. It really depends on what you use to measure it. Okay, if you're shooting light through, let's say you've got light waves shooting it through two slits, as we've seen before, you get an interference pattern. That's characteristic of wave behavior. If you were to shoot high-frequency light at a metal surface, you will get electrons emitted. And in this case, light behaves as a particle, as photons. So the light comes in as little chunks of energy called photons that interacts with the metal and the electrons in the middle, and those electrons get emitted. And to explain the photoelectric effect, Einstein made three assumptions, okay, back in 1905. First assumption is that light consists of photons, as I mentioned before, with energy given by E equals HF, which is equal to HC over lambda. Second assumption, there is this one-to-one interaction between photons and electrons. In other words, for every photon that comes in, one electron is emitted. Number 3, there's a specific amount of energy known as the work function. Okay, typically labeled as phi, Greek phi, that's needed to eject an electron, okay, from the metal surface. Okay, this was very important, this third point, this third assumption, because experimentally you could determine the amount of energy being required to eject an electron. This allowed experimentalists to test out different parameters and measure stuff. And different metals, I should mention, different metals have different phi. They've got a different work function. Okay, it's characteristic of the metal due to how relatively tightly bound the electrons are to the nuclei making up the metal lattice, right? So I should say the lattice making up the metal. So hunk of metal. Now, if you think back to junior science, if you recall, metals are made of the sea of this lattice of positively charged nuclei with electrons that are delocalized, meaning they can move right throughout the metal. That's what makes metals great conductors. And different metals have different mobility of electrons. In other words, the electrons flow at different rates, and they're more or less bound for different metals. So that's the photoelectric effect, part 1.